All right, so in this video, we're going to just do a couple examples of constant acceleration equations and how to use them to see their application. So, example 1. Cart starts with a velocity of 0.145 meters per second and undergoes a constant acceleration of 0.66 meters per second square. How far away from its starting point is it after 3.1 seconds? Often, it's useful to read the question sort of backwards and see what we're looking for. So, our key word in the last sentence is how far away, which means we're looking for some final position. And then what sorts of things were we given? Well, we were given a time, that's going to be the t final, and we were given initial velocity, and we were given an acceleration. So let's do the different colors. So this is v0, and then we're given this, and that is our acceleration a. So, what things do we have? What things do we not have? Well, we have the initial position would be 0. That's implicit because we're measuring from its starting point. We have the initial speed. We have the acceleration. We have the times. We want the final position. What we don't have and we're not asked about is the final velocity. So I'd like to avoid picking an equation that has that final velocity. Our best bet is constant acceleration equation number 4, which is this one, which has no VF in it. And again, not that there's anything morally wrong with VF, but I don't have it, and I'm not interested in it, so finding it would be potentially extra work, and I can save myself some grief by not doing that work. Well, I do actually seem to have everything else. If we take a quick look around here, we were looking for its final position, we were given its initial position, we were given its velocity and the time, given the acceleration and the time. So everybody is given, and I can just throw numbers in, and then it's just kind of uninteresting grunt work. A couple of things to note, although they're not particularly important. Note that the seconds here cancel, yay, and that this seconds squared cancels that. So we're in meters the whole way, which is a good reality check to make sure things are going fine, and we get 7.5 meters. Example number 2. A toy car moves along a line. At t equals 0, it is 2.1 meters rightward of the origin, but moving 0.8 meters per second leftward with a rightward acceleration of 0.55 meters per second square. Part A says at t equals 2 seconds, how far is it from the origin and on which side of the origin? And B, when does it come to rest, if ever? So again, looking backward here, we're again looking for how far from the origin. That is definitely still, we want an XF, and we are given TF. We're also given the initial position, the initial speed, and the acceleration. Notice that it is moving leftward, even though it was originally, we were given that it is to the right, but moving leftward. It's generally not a bad idea to have at least some picture. So here we have our flag and the car, which was, it is to the right, but it is moving leftward, but it is accelerating rightward. So that's a quick sketch of what the situation looks like, and we'd like to know where does it end up and what time does it take before it comes to rest. For A, we do have the starting position, the acceleration, initial velocity, and time of motion. We want the final position, but again, we do not have nor do we care about the final velocity, so we use CA for again, and we just throw it in. We have all those sources of information. Do note, and it's important to keep in mind, that we have negative velocities because it's moving leftward and it is to the right. We could change that around. You could be an iconoclast and say, I'm going to call rightward as the negative, in which case the initial position would be minus 2.1, but the velocity would be plus 0.8. Doesn't really matter. Just by convention, pick one and stick with it. All right, if we ground all of that in, we get x is minus 2.26 meters. So that says that it is 2.26 meters and is on the leftward side of the flag. For part B, we want to remember that at rest means 0 speed. Actually, that's a little bit wrong. It means 0 velocity. It's a little stronger than 0 speed. Also, 0 speed and 0 velocity will happen at the same times. So we have Vf equals 0. We also have the initial velocity, and we have the acceleration. We do want the time, but we neither have nor desire any position information. Notice there's nothing in here about a where, just when does it happen. So we can use CAE1, the thing that has no position information. And then it's a relatively straightforward problem again. Again, notice that we're going to use the negative time or negative velocity because it's moving the other way, which is good because in the end we want our final time to come out to be positive. It should stop after it started. And if we didn't have that flip of the sign, we wouldn't have had that. If we weren't careful and we didn't put the minus sign at this location, then we'd have gotten a time that was negative. And although technically a negative time is not a problem, here t is assumed to be after 0. It stops later than it starts. And so we should get a positive time. We get 1.545 seconds. Example number 3. A. Alice is driving at 20 miles per hour, which is given as 8.9 meters per second, when she hits the brakes, which give her an acceleration of 1.3 meters per second squared, opposite to her velocity. What is the distance L that she travels before stopping? Part B says Bob is driving an identical car at 40 miles per hour, that is 17.8 meters per second. The brakes apply the same deceleration. How far does he travel? And we have an example for case A. We have a sketch here where we have the car. It travels some distance L and stops. And so we have some initial velocity, and it ends with no velocity because the acceleration points the other way. And we say that x equals 0 is when we apply the brakes, x equals L is when we come to rest. In part A, we're looking for what's called the stopping distance. That is literally the distance over which it takes the car to stop. We're given the initial velocity and acceleration, and we're implicitly given the final velocity because the car stops, right? It has v equals 0 at the end. And note, that's a trick that happens a lot in any kind of physics testing environment where we look for ways to give you values without actually writing the numerals, especially values of 0, right? So we say like at rest instead of saying v equals 0, but it's the same thing. Sometimes the same thing where we say at the origin instead of saying x equals 0. It's a way of burying some stuff in the words and not having as many numerals on the page calling out to you. Since we want to change in distance, we can effectively set the initial position to 0 and the final position to L. That's up to us. We neither have nor desire anything about the time, so we should avoid any equations that involve t. Our best choice, therefore, is CAE5. And we look over here how that solution is. All right, blah, 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 and we write it out. Right, we solve this over. Notice that we algebraically, or something which I do a lot, is I actually solved the algebraic equation first and then put numbers in. You can do it any way you want, although we're going to see in a second my way is better, or at least in this case it's going to pay off for us. The distance for that the car stops is 30.5 meters, which is pretty far. It's about a third of a football field. You'll also notice that in writing my equations, I wrote the acceleration as minus a0, where a0 was 1.3 meters per second squared. We write a0 is therefore the magnitude of the acceleration, and the minus sign is its direction explicitly. This isn't required, although I think algebraically it works out nicely. If you can force your symbols to be positive, then your brain will function better. We're not so good at negative arithmetic. All right, for part B, we could just grind away in the same manner, right? We could set everything up. The setup is the same, so the solution would look the same. But we can be cleverer here. We can notice that we semi-accidentally derived a relationship between the stopping distance and the initial velocity. That was, again, this thing. That if you give me the initial speed, then I can find the stopping distance. Since that would hold for Bob, and Bob's speed is exactly twice Alice's speed, then I can do something like this. I say that Bob's stopping distance is his initial speed squared over twice the acceleration, but his speed is 2v0, so then we square that and we get 4v0 squared over a. But this thing in parentheses is Alice's stopping distance, so Bob's stopping distance is 4 times that. And that's a useful trick. It will save you a lot of grief on the AP exam if you can start looking at the forms of this thing and saying, oh, the A doesn't change and the V is doubled, so the L is quadrupled. That kind of thing. Example 4. A small rocket propels a box from rest across a frozen lake. The rocket fires for 3 seconds and provides a constant acceleration of 2 meters per second square. Once the rocket burns out, the box moves at constant velocity. How long does it take the box to arrive at a distance of 25 meters from its starting point? As always, it's good to sort of at least sketch out what's going on here. So I'm going to draw this, and here's our box, and there's, for whatever reason, a rocket on it, which gives the box a forward acceleration. The box travels for some distance over some time, and then the rocket shuts off. Oops. But at this point, the box is moving, and then from then on it moves at that same speed, where a equals 0. And the key thing, first of all, is this is not a constant acceleration case, because a is non-zero, and then later it is 0. So you're like, oh no, how can we possibly do applications of constant accelerations if there's not constant acceleration? And we can't, except we can play a trick. Because at this moment, we have constant acceleration everywhere between the lighting of the rocket and that moment. And then after we have constant acceleration, happens to be 0, but we again have constant acceleration. There's a discontinuity here, and so our equations don't work through that moment of time. But the velocity and time that we have here at the end of our first motion becomes the initial velocity and position we have at the start of our second motion. So this is a case, again, where we can take a complicated motion and split it into 2 relatively straightforward motions. All right, here I've cleaned up and given everybody names because names are power. So we start at 0 seconds, 0 meters, and 0 meters per second. And then I'm going to say during the acceleration, it takes t1 time, which is 3 seconds. They gave us that, at which point we reach some position x1, and we have picked up some velocity v1. I don't know those yet, but I can start talking about them by giving them names. And then they become the initial moments of this acceleration, or right where the acceleration happens to be 0, so this motion. And I can get these. At the moment, we're going to focus on the first bit. So currently, I'm talking about this interaction. And so I can figure out what v1 would be, because we know that v is v initial plus a times the time. So looking here, we have v initial plus a times the time. That ends up being 6 meters per second. And likewise, we know that the position, if we have all the things and we don't need the final velocity, our position is this parabolic thing. We throw in those numbers, and we get 9 meters that come out. So at this point now, the end of this problem in the box, this mini problem, is 3 seconds at 9 meters, moving at 6 meters per second. So I put those in here, and now I'm going to consider this box, this solution. And here, our final velocities have now become our initial velocities. We have initial position of 9 and initial velocity of 6. We are happily in a case where a equals 0. That's going to make life easier. And so I know that the final position, we're going to use the equivalent of a thing that looks like that final position is initial position plus initial velocity times time plus 1/2 the acceleration times the time squared. That's 0. Well, it's 0 because we were told that the acceleration is dropped to 0. And then we have the time is tf minus ti. And the initial position is what we were given earlier. And the final position is L. So we end up with this equation. That my final position is my position at the start of the second part, at the point where the rocket has burned out. That position plus the speed that I had at that moment times the time that elapses, but we have to take off these 3 seconds because we're not starting our clock there. Remember, I started clock way back when the rocket fired. So the final time is going to be the initial time, or the time to reach this initial point, the burnout time of the rocket, plus this expression. And when all is said and done, we get 5.7 seconds. So it takes a total of 5.7 seconds to go a total of 25 meters. Notice that the first 3 seconds, or roughly half of that time, it only moves 9 meters, and then the second half it moves basically almost 3 times as far. And that's because it's already moving very fast, even though there's no more acceleration.